We would now like to study the properties of what happens when we put a current loop in a magnetic field. So for simplicity, the current loop that I'm going to look at will be just some type of wire. So we have a current I on all of these legs, and that's our current loop. And what I'd like to ask now is what happens when we put this current loop in a magnetic field. And for simplicity, let's just indicate our magnetic field B, pointing like that. And now, when we begin to make the analysis, we've already studied the example that we're going to look at is B is uniform. And when we know that we put a uniform current loop in a current loop in a uniform magnetic field, then the force on that loop is the integral of I ds cross B. But because B is uniform, I can pull that out of the integral, cross B. And the integral of ds around a closed path is 0. And so the force on a current loop in a uniform magnetic field is 0. But what about torque? Now, we want to consider torque on the loop. And because the force is 0, we can choose any point we want in which to calculate torque. So if the force on the loop is 0, it doesn't matter what point we calculate torque about, we'll get the same answer. So let's draw our loop here. And we have a current I. And we have a uniform field B pointing this way. So we have a current going around the loop. And what we have to calculate is the force on each leg of the loop, which is definitely non-zero. Remember, a force on a leg of a loop is the current I ds through that leg cross the magnetic field. So when we look at that, if we label this leg 1, 2, 3, and 4, we see that this force on legs 2, I is in the direction of B, and remember, the ds is always in the direction of the I, and let's just make sure that we can see this. So we have leg 2 here. We have the current I, and the ds is pointing in the direction of I. Here, our I is pointing in the opposite direction, and our ds, if we calculate ds going around this loop, the ds is that way. And in both of these legs, the force is 0 because the ds is parallel to B. So the force on legs 2 and the force on leg 4 are 0. Now, in leg 2 and leg 4, we do have forces because we have the ds going this way and a ds, say, going down that way in the direction of the current. And so what we want to do is calculate the forces on those two legs. Now, let's think about that calculation. So the force on leg 1 is equal to I ds1 cross B. And when we make a calculation like this, let's just choose a set of unit vectors to make things a little bit easier. That's our little df. And we get I. Now here we're going in the j direction, dy j hat, cross B I hat. And when I take j hat cross I hat, remember I hat cross j hat is k hat. So j hat cross I hat is minus k hat. We get minus I dy b k hat for the df1. And when I integrate that around the loop, around this leg, let's put some dimensions in here. We'll call this a width w, and here a length d. So I'm just integrating along this length. So it's just the integral of dy is minus I wb k hat. So on this leg, we have a force that's in the minus k hat direction. So we have that force F1. Now, without repeating this whole calculation, the force on leg 3, well, leg 3, the only thing that changed was the direction of ds. And on leg 3, ds is pointing down, so we'll get a change in sign. So we get I, W, B, K hat. And that's a force on leg 3 coming out of the plane of the figure. When you add these two things together, you get 0, 0, corresponding to the idea that there's no force on this loop. But torque is a little more complicated, because when we talk about torque in general for any particular leg, it's the integral of some vector from some point to that leg times a little df on that leg. And then we're going to add this up over the legs. So now we want to calculate this torque, and what's important is to have a good coordinate system. So I'm going to start again and think a little bit about choosing a smart coordinate system. Well, on this leg, the force we saw was into the plane of the figure. And over here, the force was out of the plane of the figure. We had I hat, J hat, K hat coming out. We had a current I in this loop. And I'm going to choose a point P here to look at the force. Now, in general, torque is some RP across the leg. And I'll do this calculation first a bit simply. I'll just assume that the whole force is acting at P. And that's why I chose P in the middle of the leg. Then the torque total about P is the torque on leg, we call this leg 1, remember? Leg 1, about P of leg 1, plus the torque of P about leg 3. And this one, when we put all the force acting at that place, is 0. But if you think about it, if the force is always going into the plane of the figure, then the r vector for a point down here is exactly canceling the r vector for a point up there, and so torques will cancel in pairs. So the idea that the torque on that leg is 0 makes sense. Now, for leg 2, let's once again just say that the whole force, which is coming out of the plane of the figure, F3, is acting here. And our vector from RP to this point 3 is there. So what we have is simply the vector RP3 cross F3. And let's write that out. R3, we had a distance that this was length D, and this was W. And so we have D I hat cross F3 was I, W, B, K hat. And I hat cross K hat is minus J hat. So we get I times W times D times B in the minus J hat direction. And that is the total torque. As an exercise, you can calculate what would happen if you just took a little element and integrated from one side to the other to get the torque on all of these little pieces. You'll get the same result. Now, let's think about our loop again. And this is where the magnetic dipole comes in. Our loop has a current like this. We had I hat, J hat, and K hat. And our magnetic moment, by the right-hand rule, as you look at this loop, N hat, right-hand rule, is into the page of the figure. So our magnetic moment, mu, remember, it's in the direction is perpendicular to the plane of this. It's the current times the area, which is WD. Now the direction into the plane of the figure here is minus K hat. So that's our magnetic moment associated with this current loop. And now, when we want to calculate the total torque, we want to look at it in terms of our magnetic moment. So what we want to define a definition of torque on a current loop in a uniform magnetic field is mu cross B. Now let's see if it corresponds with our calculation. For our current loop here, we have the dipole moment pointing in the minus k hat direction. Our magnetic field is pointing in the I hat direction. So the B field was going in the I hat direction. And k hat cross I hat is negative j hat. And so we get I omega d B in the negative j hat direction. And that's exactly what we calculated. So this is the torque on a current loop in a uniform magnetic field, and we refer to it as a torque on a magnetic dipole in a uniform magnetic field. So here for this calculation, B was uniform, and that's how we made this calculation. So that's our first calculation about torques on a dipole.